The curses of putting the videos up on YouTube is that the class attendance tends to dwindle. I noticed this. The more convenient we make it for people to watch videos. Announcements. Let's see. You have a homework due a week from yesterday. So if you really haven't started that, I definitely would suggest that you do. We have lots of office hours. We have a total of 5 office hours each week if you guys need help. And there's also Piazza. Let me just look when the project proposals are due to remind myself. So the project milestone says is due at the end of this month, according to the website, September 29th. If you guys have not thought about that at all, you should also definitely do that. So at this point, you should be contacting other people in the class, trying to form groups of 2 or 3, and starting to, hash out some project ideas. The milestone, which is due at the end of this month, it's not really that big of a deal. We don't give people bad grades in the milestone unless they don't do it. So if you turn in something, even if it's not a very viable project idea, that's the point of the milestone, is for us to be able to give you feedback. So don't stress out about it, but make sure that you do something because we want to give you feedback. If your project idea doesn't really seem very feasible or related to optimization or something, we'll tell you that. Any questions on administrative stuff before we start? No? OK. I wanted to go through a few more slides from the last lecture, like really one example in particular that I think is kind of neat. And then today we have a fun lecture on all the various kind of canonical forms of convex programs or convex problems that you might encounter. OK, so we saw this idea last time. I just was going to leave it up on the slide for a minute because this idea of slack variables we're going to see today actually helps quite a lot with reformulating LPs, QPs, SDPs into what we call standard form. So just a quick refresher, if we ever have affine inequality constraints, we can always turn those into affine equality constraints by introducing what we call slack variables. So the general idea is if you have gi of x is less than or equal to 0, you can rewrite that as gi of x plus si is equal to 0, or si is a new variable you've introduced, and you just put a non-negativity constraint on si. These two together are the same as this. But you can see that when gi is affine, this entire thing is just a new affine constraint, equality constraint. So it says that you can kind of get rid of affine inequality constraints in favor or in trading off for more equality constraints and simpler inequality constraints that are just non-negativity constraints. So this was a few other kind of transformations we didn't get to last time for convex problems that I wanted to go over, and then an example. If you give me an optimization problem that's of this form, minimize f of x subject to x being in some set C, which remember we said this is like, it's perfectly general. This form of the way that we write this can encapsulate all the inequality constraint functions and equality constraint functions in this set. Then if I take a bigger constraint set called C tilde, so if I actually just enlarge the optimization constraint set, then we call this a relaxation of the original problem. That's typically the word we apply to it. And its optimal value is always going to be smaller than or equal to that of the original problem. OK, so that should be clear because we're minimizing f over a larger set. The value we get can only be smaller or equal to. Oftentimes, we do this when the original constraint set is not convex. So we would call that a convex relaxation. For example, we might take the convex hull of C, and that might be our C tilde. That would be called a convex relaxation of our problem. And what we know in doing that is that the optimal value can only get smaller, or it can stay the same. OK, that's the idea of relaxing the constraint set in some sense. And a typical case you might consider is when you have non-affine equality constraints. So you have equality constraints, but that aren't determined by affine functions. Remember, we can actually fit this into a convex problem formulation if these aren't proper affine functions. So if we would relax those to inequality constraints, if these functions were convex, that's perfectly fine. We now have a convex problem. But we may have actually changed the problem. It could be the optimal value of this problem now convex is smaller than what it was before. If we're lucky, maybe it stays the same. Right? It just depends on the problem. So I have an example in the slides. We went over this last time in detail, the last version of this course, and we actually had homeworks on it and stuff, but it would turn out to be actually quite a bit more subtle problem than I initially thought it would be. So I'm just going to kind of give you the very high-level explanation of it. If you're curious to learn more about it, go over the slides and homeworks from the last version of this course, or check out Boyd and Vandenberg. I think it's going to be the chapter on just convex optimization, which is probably going to be chapter 3 or 4. I can't remember which one. The one that introduces optimization problems also has an example of this form. The problem that we're looking at, let's suppose, is a maximum utility problem. So it models what happens if you, are trying to basically handle a bunch of investments. And the variables in this optimization problem, let's say, are x and b. And the criterion in this optimization problem is the sum of alpha t u of xt. And you can think about xt as the amount that you've consumed of some good at time t, and u as a concave utility function. So it tells you what you get out of consuming some amount. Alpha t are given to you. They're just think of them as positive weights. So this entire function then is concave, right, in x. So it makes sense to maximize a concave function. And what we can see just briefly staring at this is that these constraints almost look like convex constraints. This almost looks like a concave maximization problem. Okay, except this is the troublesome constraint right here, this equality constraint. So let's just first look at the inequality constraint. We're telling ourselves that the amount consumed at each time point has to be somewhere between 0 and bt, where bt is our budget. Okay, another variable. So you can't consume more than you have available as part of your budget. And then we have this recursive definition for bt, which tells us that the budget at time t plus 1 is what it was at time t, minus the amount that you've consumed, plus some investment return function. So suppose I make some investments with my budget. What I get back out of that is fb of t. So what I have as my new budget is the amount I've consumed, x of t, the amount I've gotten in return for my investments, and what I had before. This should make sense just at a high level, this recursion. And so that this convex, or this nearly convex problem, is trying to figure out the optimal allocation of your budget and consumption over, say, capital T time steps. This is not a convex problem because of this constraint. We didn't tell you that f is an affine function, and if f was not an affine function, then you'd be in trouble, right? Because I have a non-affine equality constraint. I can think of, let's just think of f as a concave function that's increasing, okay? So like, say, square root of x, or square root of bt. That's f of bt. So it turns out with this problem, if we replace the equality constraints with inequalities, then that is a relaxation of the original problem, as we mentioned per the last slide. The new problem is a concave maximization problem, or a convex optimization problem, we'd call it. And the nice thing about this particular example is that it doesn't change the optimal value of the problem. It doesn't actually change the solution either. So to see that, it requires a little bit of manipulation, which is why I decided not to do it in this year's course. You can take a look at the homework. Actually, homework 1 from last year's course goes through this in detail. The intuition is that it doesn't help to throw away money. So if at the solution, for some reason, your budget was just strictly less than what you had before, plus your investment, plus your consumption, that wouldn't be helping you out. So you'd be throwing away money in some sense. So you might as well take your budget as large as you can, determined by the investment, what you had before, and your consumption. So we can always relax that to an inequality constraint, because at the solution, we claim, at least intuitively, this is going to be tight. We're going to see an equality at the solution. So we haven't actually changed the problem. Okay? So that was just a high-level explanation. The idea is a simple one, right? Sometimes we can relax equality constraints to inequality constraints, and if we can argue that they're actually tight at the solution, then we haven't changed the problem. This is the example I wanted to go over more so than the last one. Another example of relaxing an equality constraint. I think it's a really cool one that a lot of people maybe don't see or just aren't familiar with, because we typically think of principal components analysis as being very non-convex. So let's suppose I give you an n by p matrix, and I ask you to form a low-rank approximation of that matrix. And I ask you to solve, in particular, the following problem. Find me a matrix R that in Frobenius norm is closest to x. Frobenius norm between matrices means just the sum of the squares of the absolute values. So it's like the L2 norm but for matrices. Or it's literally the L2 norm if you unravel the matrix into a big vector. So find the matrix R that's closest to x in Frobenius norm but that has rank k. Okay, so this is the best rank k approximation to my matrix X. This is a very kind of well-known problem in terms of PCA or the SVD. The solution, as you probably would have seen in other courses or maybe would have heard, is just to take the singular value decomposition of X, UdV transpose, and to chop it off after the first k singular values. So essentially, you can think about it in multiple ways, but let's suppose I just take the first k columns of U. I only take the first k diagonal elements of D. And I take the first k columns of V as well, which means the first k columns of the first k rows of VK transpose. So I basically throw away everything after the first k singular values. And I form this new product, UK, DK, VK transpose, and I call that R. That is the solution to this problem. Okay, and when the SVD is unique, which happens when there's no ties, let's say, in singular values, then this is the unique solution. So it's pretty cool that we know how to solve the best rank k approximation problem exactly using the SVD. You might also call this its reconstruction from its first k principal components, right? Because if I thought about this in terms of PCA, then the columns of U are the principal component directions. So I'm taking the first k directions that explain the most variance, let's say, in my sample. So I'm reconstructing X from the first k principal components. This is not a convex problem. It's very far from a convex problem. What makes it non-convex? What is it, sorry? The rank constraint, yeah. So why is rank not a convex function? Give me an example of why rank is not a convex function. Yeah, sure.
A plus minus A is 0.
It's a good example. So yeah, the example was if I have, let's suppose I have some matrix A of any rank that's, so that suppose A is not trivial, and I take another matrix minus A. If I take a convex combination of those, let's say half A plus half minus A, I'm going to get 0, which has rank 0. It's clearly not going to obey no, actually that's not quite going to work, right? Because what we want to see is that actually the rank gets bigger when we add two matrices. So we want to see that rank of, let's say, alpha A plus 1 minus alpha B exceeds the rank. Right, we want to see this violated. So how would I do that? Yeah.
You have two 2 by 2 matrices. One of the first column is, let's say, 1, 0. Yeah, and that's 0, 0. And then you have another one that's 0, 0, and 0, 1.
Right. So that'll do it, right? Because these are each rank 1. If I take any convex combination of them, they're rank 2. But the right-hand side is always just going to be 1. So it's certainly not convex. In fact, the way you can think about the rank on matrices is that it's analogous to the L0 norm on vectors. So it's about as far away from a convex function as you can imagine. So it's very non-convex. Right. So we're going to actually do a few things to manipulate this and to take a convex relaxation. We're going to want to relax this constraint set. So the way we're going to do that is we're actually going to first kind of reformulate the problem in an equivalent form that's non-convex. And then we're going to take the convex hull of the constraint set. So we're going to write this as, find me a projection matrix that's a k-dimensional or rank k projection matrix on which I can project X and then measure the Frobenius norm between X and XZ. It's really an equivalent problem. The solution to this problem would just be VK transpose, for example. So it'd be forming the projections from the first k principal components. So it's an equivalent problem. What does it mean for a matrix to be a projection matrix? Let's spell out this constraint set a little bit more carefully. It means that Z is let's say a P by P matrix, symmetric. And there are two kind of defining properties of or there's actually one defining property of a projection matrix besides symmetry. And then the second constraint is to do with its dimension. It's the rank of that projection. A projection matrix always has eigenvalues that are either 0 or 1. So if a matrix is symmetric and it has 0 or 1 eigenvalues, then we call it a projection matrix. And this just determines its rank. The sum of the eigenvalues, in this case, is just the number of non-zero eigenvalues because they're all just 0 or 1, right? So its rank is going to be the sum of the eigenvalues. And so enforcing that trace of Z is equal to K is just saying that Z has to be of rank K. So this is our constraint set. So now that we see this, it's interesting. It's not, at this point, it looks like it's certainly non-convex. It's really the same constraint set as we had before, just reformulated. But we can kind of see what to do. Informally, what happens if we just relax the eigenvalues to be between anywhere 0 and 1, not just 0 or 1? And is that an offensive constraint, the trace C equals K? What is trace as a function of Z? What kind of function is that? Yeah, but what kind of function is that as a function of Z? Just a linear function, right? Just summing up the diagonal entries, so it's a linear function. That should make sense to you. That's a linear equality constraint on a matrix. So that's actually not bad at all. It's just this one. And now we might think, well, let's just relax the eigenvalues to lie between 0 and 1 rather than be equal to 0 or 1. You can check that by doing so, you've actually formed the convex hull of that constraint set. So this might be a good exercise to make sure you understand convex hulls. Prove that that is the convex hull of this. So just by making that an interval 0, 1, we've actually formed the convex hull. We can also rewrite that just in the simpler form. Z has to be between 0 and 1 in matrix inequalities, or 0 in the identity. This means that all of its eigenvalues lie between 0 and 1. This is called the Phantope of order K. So it kind of looks like a polyhedron, but it's in a matrix, right? We have some linear inequality constraints on a matrix, and we have a linear equality constraint on a matrix. It looks kind of like a polyhedron. We call it a phantope just because I think it's named after this author Fan, who first kind of studied this object. So to relax that problem, the one we saw before, we can just use this constraint set instead of the one that just considers all the eigenvalues being equal to 0 or 1. And we get this new problem. Find me the projection, or it's actually not a projection anymore. Find me the matrix Z such that XZ is closest to X in Frobenius norm, subject to Z lying in this constraint set, which is bigger than the set of rank K projection matrices, because all these matrices can have eigenvalues between 0 and 1, not just equal to 0 or 1. That's a convex problem because the constraint set is convex. And remarkably, you actually get the same solution if you were to go and solve this than you would to the PCA problem. So you do not lose anything when you make this relaxation. So in a sense, PCA is actually a convex problem, or at least it's equivalent to a convex problem. It's something I think a lot of people don't see. And certainly when I actually didn't know this until a few years ago, when one of my colleagues in statistics came and told me this, that people had figured this out a long time ago, and was very excited about it. And I was shocked, because we always learn PCA as a non-convex problem. Here it's being written equivalently as a convex problem. Okay, so this is from 1949. I'm sorry?
Why it is equivalent?
So I didn't give you a proof of why it's equivalent. I just told you that it is. I just told you that in this case, the convex relaxation is tight. It's because here's my extremely rough explanation. This is curved enough, this loss is curved enough, so that the minimizer always lies at a vertex of that constraint set. So it's never going to lie on a, so this constraint set, think about it as a polyhedron for matrices. Its vertices are kind of determined by this set, right? The set of matrices that have eigenvalues equal to 0 or 1. And it works out, if you take a look at this paper, that the solution, if you solve this problem, is always going to lie at a vertex. It's a really nice result. And it started now a whole kind of slew of work on sparse PCA out of some of people in statistics here at CMU who use this as a jumping point for sparse PCA, because now you have a convex problem to sparsify. So if you're interested in that, then you can take a look at some papers by Jing Li and Vince Fu. They have some very nice papers on this. All right. Any questions about that? Yeah.
So for the original PCA, you're using SVD to get the solution, right?
Yeah.
But you see, you can get a convex flow for this problem. So is there anybody like try to solve the PCA using convex optimization?
That's a good question. So you'll see today, actually, from our lecture today, that this is an STP. And I would say, in general, STPs, unless they're very special, are harder to do than a single value composition. They're not a very easy problem to solve. This one, I think, is probably an example of that, falling into like a generally hard STP. So I'm not familiar with people using like interior point methods or something to solve this. But when you do sparse PCA, you need to use that. So there's not like a very simple SVD-like formulation you can use.
Are there any pathological cases where that's not necessarily equivalent? Like, is it equivalent with probability 1, or is it guaranteed always equivalent?
Good question. I actually don't know. I would guess that in pathological cases, this has multiple solutions. And one of them is going to be a solution to the PCA problem. But I don't know for sure. I would take a look at either this paper or some of the newer ones. Yeah?
So what's the advantage of using these formats compared with the canonical proof? You have a constraint of W such that you use like Lagrange multiplier and basically prove the W, the original form.
I'm sorry, I didn't really understand the question. Proof meaning that the PCA, that the SVD gives you the best rank approximation?
Like you could have a covariance matrix of the data and use W transpose covariance matrix times W. You want to maximize that such that the W transpose W equal to 1.
So that's like a sequential way of looking at PCA. Find the first principal component direction, the second principal component direction, etc. Yeah, this problem is telling you what they all are at once. It's just it encapsulates that the first case, that's that problem into one optimization formulation.
So is it like in the future, if you want to prove any like low rank approximation problem, maybe this is a better way to do it?
Well, the fact that it's convex is a big win. So I said this, maybe I said it rather quickly. People didn't really realize that this fact was true, I think, or didn't appreciate it until a few years ago. So there's been a lot of work on sparse PCA. How do you get principal component directions that are sparse? But everyone went from the non-convex formulations in order to sparsify the criterions. So for a long time, I'd say probably 10 years, people were taking the sequential problem, the one you mentioned, or the rank K approximation problem, and they're adding kind of sparsity constraints. But they couldn't really do much with it because the problem wasn't convex. So the solutions that they were finding were all locally optimal. And it's harder to characterize also theoretically what you get out of it because it's harder to understand non-convex problems. When people realized that PCA was equivalent to the convex problem, namely this one, sparsifying it is actually much, much easier, right? I can add an L1 penalty at this point to Z, and that still is a convex problem. So both computing the solution and also understanding its properties became a lot easier. So it kind of led to a breakthrough, I think, in sparse PCA. No, yeah. So yeah, good question. So once you apply a penalty, the solution is going to lie somewhere not generally on the vertex of that constraint set. So it's no longer going to be equivalent to the exact rank K formulation. Yeah, there's like a strict discrepancy. Good question. All right, cool. So let's get to canonical problem forms. I think this is going to be a fun lecture. So last time we went over, I'll just very briefly say it, optimization terminology, properties, and first order optimality. This was like the big thing we learned, how you can characterize the solution to a smooth convex function if it's to a smooth convex problem if the criterion function was smooth. Remember we had a formulation for that. And then a bunch of equivalent transformations that we saw at the end, including relaxations, which we just talked about. So today we're going to talk about LPs, QPs, this is SDPs, and cone problems. And when I taught this class last year, I had this particular lecture, I had Javier Pena, who's an optimization expert in the business school, give a guest lecture, and he drew this cool picture, and so I want to redo it. I thought it was a motivating picture. I may even make it a bit more dramatic than him, just to one-up him. So here, let's suppose this is the world of LPs. Okay, so you're happy and you can solve all these LPs. Turns out that LPs are a special case of QPs. Okay, so this might be what it looks like. And by the way, there's nothing rigorous about this picture. This is completely hand-wavy. But it gives you a sense for the lay of the land. QPs are a bigger problem class. They are substantially harder than LPs. And you'll see examples of an LP and a QP, and you'll see that actually the QPs that we mentioned can be pretty hard. Then there's SDPs. And SDPs kind of look like this. So this is really the big difference. The jump from QPs to SDPs is massive. SDPs are a way bigger problem class, and they are way harder than QPs. So there's really no comparison. A generic SDP is very, very hard to solve, even though it's convex. Okay, so I would say, heuristically, an SDP with more than 1,000 variables is getting to be almost intractable, unless it's a very special SDP. Whereas an arbitrary QP, we can handle for hundreds of thousands of variables. It's not a problem at all. Okay, so SDP is a lot harder. And then there's conic programs, which are even bigger than SDPs. If you use CVX, which you are going to learn to use on the first homework, if you use some like optimization solvers like Sedumi, these other kind of general purpose optimization solvers, they formulate everything that you give them as a cone program, and they solve it. So this is where I think things get hand-wavy. This so far was, obviously there's nothing rigorous about these sizes, but I think this is intuitively more or less the case. I would claim that cone problems are very close to the set of convex problems. It's pretty hard sometimes to find convex problems that aren't cone problems. You can find examples, but like I said, general purpose convex solvers turn everything that they can into a cone problem, and they're very successful at doing so. You can usually use CVX or something like that for almost any problem that you might encounter. So I'm going to draw this as a dotted line because I'm not really sure how big to make it. But somewhere out here is the set of convex problems. Okay? And then just to give you some perspective, this is maybe the set of convex problems among the set of non-convex problems, or just optimization problems in general. So it's kind of like if you were studying the stars or something, and somebody showed you Jupiter next to Earth, and you were blown away. Then they put the sun next to Jupiter, and you kind of lost it. That's what's happening here. So we're not really solving that many problems in the grand scheme of things, but this is the hierarchy nonetheless. Okay, so that was my picture. So let's start off with LPs. A linear program is an optimization problem where the criterion, the inequality constraints, and the equality constraints are all linear functions or affine functions. Okay. This type of problem is always convex. You can't make it non-convex no matter how pathologically you try to choose these matrices or these vectors, right? Because I always have an affine criterion, which is always a convex function. I always have affine inequality constraints and affine equality constraints. It always makes a convex optimization problem. I can have this being a min or a max. It's still going to be a convex optimization problem. Okay. I I think people remembered Danzig for LPs in the 1940s. Danzig was the guy who invented the simplex algorithm, became very famous for that, among other things. But so I'm told Kantorovich actually studied LPs earlier than Danzig in the late 1930s. We're not going to learn the simplex algorithm in this course. We taught it in previous versions, but I just didn't think that it was something that people really got a lot out of. It's a very beautiful algorithm, but it's very specialized in a sense to LPs. The one thing that I would say it's important to note about it is that it's a direct algorithm for solving LPs. So pretty much everything we're going to learn, starting when we talk about gradient descent onwards, so all the algorithms you're going to learn in this class are what I would call indirect or iterative algorithms, which means that you iterate the algorithm, and as you iterate, it gets closer to a solution, and you get some guarantee such that if you wanted the points you're going to settle on to be epsilon close to the solution, you need to take this many iterations. Right? So in the limiting case, you're going to get the solution exactly, but you're going to be kind of epsilon away after 1 over epsilon iterations, that kind of thing. Direct algorithms are different because they give you the exact solution of the problem up to computer precision. So it's a very different class of algorithm. In a perfect computing environment with no kind of overflow or round-off errors on a computer, the simplex algorithm would give you the exact solution to an LP. But say an interior point method wouldn't. It would never give you the exact solution because it's iterative, and it would just get you closer and closer, even in a perfect kind of computing environment. Okay, so that's the distinction. Sometimes people prefer direct algorithms if they really want a super high-quality solution. We won't see very many of them because they tend to be specialized. So this is a very fundamental problem in convex optimization. It was kind of the original problem that people spent a lot of effort studying. There's lots of history and diverse applications of it. I'm just going to go through a few simple examples. The diet problem, I think it's a fun example. Let's suppose that x is a variable that contains the units of food for each kind of type of food you're going to be consuming as part of your diet. So xj is the units of food j that you're going to consume. So let's consider this problem. Minimize C transpose x subject to an inequality constraint. Dx is bigger than or equal to little d, and x is bigger than or equal to 0. So this makes sense, right? You can't consume negative units of food, or at least that would be pretty bad if you were doing so. Let's suppose that another constraint is that for each nutrient I, you need to get that many nutrients in order not to get sick. Okay, so you don't want to just eat Cheez-Its all the time, even if you find them delicious, because you can get sick. So you have some constraint that you have to actually consume so many nutrients. Then each row of D is going to basically tell you how much you get out of consuming the various food types of that particular nutrient. So that's a nutrient requirement. And Cj is the per unit cost. So this is just saying I want to spend the least amount on food subject to meeting all my nutritional requirements. So classic problem for LPs. The transportation problem is also a classic problem for LPs. I'm just going to skip it because we have lots of examples. But this one, I think, was a problem that people actually studied for practical reasons when LPs were first kind of coming out. Here's a non-trivial problem that fits into, I mean, these are also non-trivial, but here's a problem that fits into LPs that maybe you might not see right away why it's an LP. Let's think about solving a linear system of equations. So x beta equals y, where beta is the variable, and asking for a sparse solution to a linear system of equations. And in order for this to be interesting, we're going to assume that that system is underdetermined. So there's multiple solutions. We want to find a sparse one. The sparsest solution to a linear system of equation would be given by solving this non-convex problem. Minimize the L0 norm of beta subject to x beta equals y, where the L0 norm just counts the number of non-zero elements in that vector beta, right? So that makes sense why that's the sparsest solution to the linear system. The L0 norm is not actually a proper norm. We just call it the L0 norm, I think, being casual, but it's not a proper norm. So this is not a convex problem. Like we said, the L0 norm is very far from convex. I don't know if we ever explicitly stated that. So maybe I'll just write it down. The L0 norm of beta is the sum of the indicators that each component is not equal to 0. So let's suppose beta was p-dimensional. That's the L0 norm. Okay, Okay, so now you can see why it's so non-convex. Right? Think of the same example we have with matrices, basically. So the L1 approximation to this problem is often called basis pursuit. I just replaced this L1 norm with what I saw previously. I mean, I placed the L0 norm with this L1 norm. And this goes by many names, but some people call this the basis pursuit problem. We saw the lasso, right? This is almost like a noiseless version of the lasso. So I assume I have no noise in my measurements, so I actually do observe the target directly, and I want to find beta, the coefficients that make this equality true, but also have the smallest L1 norm. This is actually an LP, and it's got a lot of attention when people started studying compressed sensing, and even now, it's an LP. So how do we see it's an LP? We can reformulate it in a way that makes it transparent that it's an LP. We're just going to introduce an extra variable, okay, that's of the same length as beta. Let's call it z. And we're going to require that z be between, that z be bigger than or equal to both beta and minus beta in each component. Okay, so only one of these constraints is ever going to matter, and that's going to be whatever one that corresponds to the sign of beta in that component. Right, so this is effectively saying that z has to be bigger than or equal to the absolute value of beta in every component. But formulated this way, we clearly have a bunch of linear inequality constraints, which is what we wanted to do. We're going to replace the L1 norm of beta then with just the sum of the entries of z. And I actually claim these two problems are going to be equivalent. So check that makes sense to you. Think about why that's the case. So that's going to be the case because it's never going to be helpful to take z to be strictly bigger than the absolute value of beta in any component, right? Because that's just going to make the criterion bigger, and the constraints would be loose at that point. So if you ever had such a solution, I would just take z to be equal to the absolute value of beta in that component. I would make the criterion smaller, and I would still be feasible with respect to the constraints. So I would have gotten a strictly better candidate than your original proposal, which tells us that actually at optimality, z is going to be basically equal to the absolute value of beta in each component. So these two problems are going to be equivalent. Yeah?
So the reformulation makes sense to me. I was just wondering, why is the first one not already a linear program? I have missed that.
Linear programs have to have the criterion and the constraints all being linear functions. This is not, right? This is the sum of the absolute values. So, I mean, as you can see, you pretty much can always transform absolute values into linear functions, but as we've written them, they're not. Another example of an LP is the Danzig selector. So now this is like getting towards what the lasso does. So allowing for imperfect measurements. Let's suppose we didn't actually think that the y we measured was exactly x beta. There was some noise. And we want to find some beta so that x beta is close to y, but beta is also sparse. This is the same problem the lasso tries to solve. But the lasso we're going to see is actually a QP. The Danzig selector is a version of kind of sparse regression that is an LP. It's still an LP. The Danzig selector was named after Danzig, but it was invented recently. It wasn't something that Danzig himself studied. So basically, all we do is we take this equality constraint in the basis pursuit problem, and we replace it by the following inequality constraint. The infinity norm of x transpose times the residual y minus x beta should be smaller than or equal to lambda. So that tells us that for every component, I should have, for every column, let's say, of x, I should have this being true. The equivalent constraint for all columns of x. Because the infinity norm is just the maximum absolute value. This is saying that the inner product of every column or every feature, say with the residual, should be at most lambda. When we have the least square solution, this is going to be 0, right? So now we're just allowing for a little bit of slack there. When we have the linear, the beta that solves this system of linear equations, this is going to be 0, obviously, but now we're just allowing for a little bit of slack there. OK, this is still an LP. We can reformulate it in the same way as the last slide to take care of the criterion. this constraint actually can just be reformulated in one more step in the following way, right? As a set of 2p linear inequality constraints in beta. So Danzig selectors, I think it's a pretty neat estimator. Lambda is a tuning parameter here. It kind of controls the trade-off between how well you want to fit to y with x beta and how sparse you want to make beta itself. Yeah?
What advantages has the Lasso formulation?
That's a tough question. Maybe we can talk offline about that. I think that, so the question was, what advantages does the Lasso have over the Danzig selector? I'm also a bit biased because I prefer the Lasso. But it's actually easier to compute the Lasso, let's just put it that. Even though this is an LP, this is actually a harder LP than the Lasso. It's kind of bizarre. So in many ways, the Lasso is easier to compute. They have basically the same theory. When this paper came out, it proved a bunch of properties about the Danzig selector that made it look really amazing. And then it spurred everyone to prove those same properties for the Lasso. So it was very good, I think, for the community. And I think it's a pretty neat idea. Yeah, so we can talk more about it afterwards if you're curious. OK, a linear program is said to be in standard form if you have a big set of equality constraints, ax equals b, and just a very simple inequality constraint, x bigger than or equal to 0. Any linear program can be rewritten in standard form. And the way you do this is to use slack variables. So I'm going to leave this as an exercise for you guys to check. Go to this formulation for LPs, this one. Introduce slack variables here. So dx plus s is equal to d. And then work that into a problem of this form. You'll see that it's possible just by introducing slack variables. So the simplex algorithm, for example, operates on this form of the problem. This one is often easier to remember. The dual of this problem is very easy to remember. It's just nice to work with standard form LPs, as it is with most problems, most of these classes of problems. OK? OK, so now we're going to move up to QPs, one step up from LPs. QPs are like LPs, but the criteria of QPs are convex quadratic functions. So I will not distinguish, in terms of nomenclature, convex quadratic program or quadratic program. I'm always considering the QPs we think about to be convex in this class. But as we saw last time or 2 times ago, this quadratic function, C transpose x plus 1/2 x transpose qx, in order for that to be a convex function, q needs to be positive semi-definite. So you could write down a problem of this form where q is not positive semi-definite, and it would not be a convex quadratic program. Okay, but since we're just not really going to study those, I'm just going to call, when I say QP, I kind of implicitly mean that q is positive semi-definite. All right, QPs allow you to express everything that you can express with an LP and more, right? Obviously, if we take q equals 0, we get back the LP, but we just get more than LPs. I have a few examples here. I guess I have 3 examples of QPs here. We might not go through all of them, but I'll try to give you some that are kind of classic optimization examples. One of the classic optimization example is portfolio optimization for QPs. So x is a variable that contains your portfolio holdings, let's say, in terms of percentages, or actually, in this case, proportions. So like 0.1, 0.15, whatever, for each different portfolio. And the constraints are that the proportions have to sum up to 1, and the proportions have to be non-negative. So those are very natural constraints for proportions. And given these constraints, we want to maximize 2 terms. The first is something like our expected return if we were to invest in those each of those different holdings with that proportion. So let's say mu is the expected return for each particular thing we're trying to invest in. And so we want to maximize the inner product of u and x. That's going to give us high expectation in terms of return. But we're going to subtract off something that has to do with the variance of our portfolio. So if Q is the covariance matrix of the asset returns, then x transpose qx is something like the marginal variance you'd encounter across all those investments. And so this trades off having a high expectation with a low variance. Right? So I'm maximizing mu transpose x minus gamma over 2 x transpose qx, where gamma is just some tuning parameter. So you're like, think about like a risk aversion parameter. Okay, so this is called Markowitz portfolio optimization. And people study this, I suppose, in finance, but I think it's a fairly basic problem. But it's a QP. That was the important point. It's a QP, right? Because we're maximizing here the negative of a convex quadratic function, so we're minimizing a convex quadratic function. OK, what's another example of a QP? I guess we have 2 more examples. I'll just say that these are QPs, and then you can check them. This one, actually, you can see almost directly it's a QP. The SVM problem we saw last time is a QP. It's because the criterion is a quadratic in the variables. I have a linear term in psi, and I have a beta transpose beta term. And all of the inequality constraints are all linear. Right, so this is also a QP. And the lasso is also a QP. I can see that in a couple of ways. So there's 2 ways to formulate the lasso problem. Last time we learned it like this: minimize the least squares error loss between y and x beta, subject to an L1 norm constraint on beta, where S would be my tuning parameter. An alternative way to parameterize the lasso is to use what we might call Lagrange or penalized form. When we learn duality, we're going to learn why these 2 are equivalent, so that for every value of S, there is some value of lambda that makes the solutions the same, and vice versa. So we'll see that formal equivalence later. But this is something that you may be just comfortable with, the idea that you can always take constraints and add them to the criterion with multipliers, Lagrange multipliers, in order to get an equivalent problem. And you can see that either of these are actually QPs. OK, so I'll leave that for you to check. This one is going to follow the logic we had for the basis pursuit problem. You're going to want to turn that into a 1 transpose z. And this one is going to be doing something similar. You're going to want to introduce some variables that have to do with the signs. Okay, but you can see that both of those are QPs. Another way of saying that is this L1 norm constraint, it's a polyhedron, right? So it's going to be given by the intersection of a bunch of half spaces. So if you enumerate those half spaces, there's just going to be a bunch of linear or affine inequality constraints. OK, QPs can also be written in standard form. It just is the same as what we saw for LPs. They can always be written in a way that such that their constraints are AX equals B for a matrix A and vector B, and a non-negativity constraint on the variable X. It's often convenient to write QPs in this form, again, for the purposes of maybe duality or sometimes algorithms, things we'll study later. Let's take a quick break, and then we'll come back and we'll do SDPs. Let's get some motivation for semi-definite programs before we actually jump into them. So remember this linear program formulation, right, where I was minimizing a linear function subject to linear inequality constraints and linear equality constraints. Semi-definite programs are born out of the idea, and actually really conic problems in general are born out of the idea of changing this less than or equal to sign to a different kind of ordering. So the orderings that we're going to do are called partial orderings, because you can't always compare any 2 elements. But that's the idea. So let's just get a bit of details for SDPs, and we'll start making sense. Just a bit of a recap of some of the notation that we've seen. Sn is the space of symmetric n by n matrices. If I write a plus subscript, then that denotes the set of positive semi-definite matrices. So these are matrices that are symmetric n by n matrices that have all their eigenvalues bigger than or equal to 0, or equivalently, U transpose x times U is always non-negative, no matter what I put there for U. So that's a semi-definite matrix, recall, which we write as, we write this as x squiggly bigger than or equal to 0. So that means that x is an n by n positive semi-definite matrix. And then Sn++, so 2 pluses in the subscript, is the space of strictly positive definite matrices. So they have all the eigenvalues strictly larger than 0, not just bigger than or equal to 0. And that means that they satisfy this positive definiteness inequality strictly, not in a non-strict sense. So for all u that are not 0, u transpose xu is strictly larger than 0. Yeah?
Is there a reason that you're explicitly calling out that the zero matrix does not belong to the set?
No, the 0, well, so I'm saying that the u can't be 0. Right, because if 0 transpose x times u is always going to be 0. Right. So some basic facts from linear algebra. I just said these out loud, but here they are formulaically. If a matrix is symmetric, then, well, actually, I didn't say this one, but this is a basic fact from the spectral theorem for matrices. If a matrix is symmetric, then its eigenvalues are going to all be real. It's going to have all real eigenvalues. If a matrix is symmetric and positive definite, semi-definite, then all its eigenvalues are going to be non-negative. So we write that as lambda x is an Rn plus. So lambda x denotes the set of, I should have maybe made that notation clear. Lambda x is just the set, it's the vector of eigenvalues of the matrix x. And if x is n by n, then I think of this as an n-dimensional vector. There could be ties here sometime, right? Or some of these could be 0. But I can always think of it as an n-dimensional vector. So this is just a nice kind of way of summarizing those facts. And if x is strictly positive definite, then its eigenvalues are all strictly positive. So it lies in Rn++. We can define the inner product over the set of symmetric matrices as follows. It's often denoted by these brackets. So x triangle bracket y, or x dot y, but the dot we usually put as a dark circle. So this is like an inner product over the usual L2 inner product over vectors. In fact, it's the exact same thing. It's just the sum of xii times yii. Xij times yij over all I and j. So it's what happens if you were to string them out into vectors and take their inner product. But I can write that more concisely as the trace of xy. So just if you haven't seen that before, then just write out what the trace of xy is, and you'll see it's just the usual inner product had we unraveled these matrices into vectors. Okay, so now I have an inner product space over matrices, and I'm going to define a partial ordering over symmetric matrices, sometimes called the Launer ordering, but we're just going to always use this ordering, so that name is not necessarily important. And if you give me any two symmetric matrices x and y, then I'm going to write x is bigger than or equal to y, if and only if x minus y is positive semi-definite. So we've already used this a bunch of times, but I'm just defining it formally. Okay, it means that the eigenvalues of x minus y have to all be non-negative. All right. So now we can define an SDP, and it's really very much like a linear program. In fact, it's exactly like a linear program, except I've just changed the meaning of that less than or equal to sign. I've overloaded it with a different partial ordering. So an SDP you can think about as a problem where the optimization variable is x, the criterion is C transpose x, the constraints are that AX equals B, everything you know from linear programming, but the inequality constraint changed. And I'm given matrices now, F1 through Fn, which are symmetric matrices. Say in d by d symmetric matrices. And I'm giving another matrix F0. And I'm saying that the matrix given by x1 times F1 plus x2 times F2 all the way through xn times Fn has to be less than or equal to the matrix F0, meaning that F0 minus the matrix on the left-hand side has all non-negative eigenvalues. That's what it means, right? That's what that ordering means. So for linear programs, for the LP world, we had this constraint, right? And if I write out the columns of D, if I write the columns of D as, let's say, dj, then this is what I've asked for equivalently. So these are the columns of D. For SDPs, I've just replaced each of these dj's and this D with a matrix. That's all I've done. So I've called them F. And now I say matrix less than or equal to, according to our order of matrices, another matrix F0. OK. This is always a convex optimization problem, no matter what F1 through Fn and F0 are. And we learned that last time, because we learned this is called a linear matrix inequality. We learned that these kind of inequalities always are convex constraints on X. Doesn't matter whether or not F1 through Fn are themselves, say, positive semi-definite. As long as they're symmetric, this is always a convex constraint set. So as I write an SDP in this form, it's always a convex problem. I claim any linear program is a semi-definite program. So I claim now that SDPs, I'm giving you this part of the hierarchy. This we're familiar with, because you just take the Q matrix to be 0. I'm claiming that SDPs contain LPs. So how do we see that? In fact, it really just comes from this. Yeah.
Just replace D with the diagonal matrix with B in the diagonal.
Exactly. So let's define, let's say, F1 to be the matrix that has just as diagonal entries, or I can even, this Fj is a matrix with diagonal entries dj1 all the way through, let's say, dj. So now I'm in trouble because I called the dimension d. So that's going to look nasty, but let's just call it R. Supposing these were R by R matrices. OK, and I made all the other entries 0. And I did the same thing for F0. I defined it just to contain the diagonal entries of this vector. Then now you can assure yourself this is true. Matrix inequalities on diagonal matrices are the same thing as the inequalities component-wise. Okay, it's because the eigenvalues of diagonal matrices are the diagonal entries. So it reduces to what you know already, the kind of usual component-wise inequality you know already. Great. So now we know that we can turn any LP into an SDP, although we wouldn't probably want to do that. We just are seeing the hierarchy. OK. Standard form for SDPs is a bit of a jump. So LPs and QPs, you guys like nodding your head like, yeah, standard form. It looks, marginally different from the other form, and the proof is just involving slack variables. Standard form for LPs looks pretty different. And when I was first learning this stuff, I was always confused about it, because the standard form involves a matrix variable, no longer a Euclidean variable. Like x here is an Rn. X here is a matrix. Okay, so standard form for SDPs in this form, they at least transparently appear quite different. But the nice thing is that both of them have very close ties to their LP analogs. So you can easily remember both of them. Right, this one we just saw the tie to LPs through this argument right here. Take a look at this form of SDPs. I've basically taken my standard form LP and I've replaced all the inner products with matrix inner products and all the inequalities with matrix inequalities. And I've just gotten the exact same thing. So C is a matrix. So instead of C transpose X, where C and X are both vectors, I have C dot X, where C and X are both matrices. Instead of having AI transpose X is equal to BI, which is one row of the constraint, AX equals B, I've replaced that row with a matrix. And now I have AI dot X equals BI. And I've replaced X bigger than or equal to 0 component-wise with X is positive semi-definite. So it's just all the matrix analogs of the standard form LP, of the lines in the standard form LP, of each of the different quantities. So I'm thinking we might put this on the homework, or if we don't, then we may come back to it in a review or something like that. But I would start thinking about why any semi-definite program can be written in standard form. It may pop up on your homework. It's not as easy as introducing slack variables, but it's also not terribly hard. You can kind of see, probably, how to go from this to this. You use the argument that was just given earlier. which is that you make capital X to be a diagonal matrix with just this x on the diagonal. And you can kind of work everything in that form. And then you have a bunch of linear equality constraints that enforce the off-diagonal elements of this x to be 0, so that it really is a diagonal matrix. The other way around, you just unravel everything here as if they were vectors. So you write c dot x as if c was some super long vector, and x, you unravel the matrix x as if it was some super long vector. And you do the same thing for these constraints. And for this, how do you write that in terms of inequality of this form? What's that? Yeah, so each of these f's is just going to be a matrix that picks out one particular component of x, right? So we're going to get that full semi-definite inequality. But write that out, or at least you can start thinking about that. That might be a homework question. So don't be startled, by the way. This is the point of this. If you see SDPs written like this or like this, because they're equivalent, even though they may look different. So some examples of SDPs. One very nice example, which I myself was not super familiar with, but Javier used it as an example last year when he taught this guest lecture, is the Lavash theta function. And it has a bunch of connections to graph theory as well. So you might have seen this in a CS theory course if that's something that you've taken. But it's a pretty remarkable paper written by Lavash in 1979. So if you have an undirected graph, G, with, let's say, nodes n and edges e, and you define these two graph theoretic quantities, which is omega g and chi of g, which is the clique number and the chromatic number of g. So how many people have heard of these quantities? I'm just kind of curious. Oh, I thought we had some SCS folks in here. Maybe everyone from SCS is being lazy and watching on YouTube. So I won't go over this very carefully then. I thought it might be interesting to some subset of the class. I'll just say what it is. But the clique number of a graph is the size of the largest clique in the graph. And the chromatic number is the smallest number of colors you can use to color the graph so that no two nodes that are adjacent have the same color. Both of these quantities are NP hard to compute. So you can't really compute them. They're just graph theoretic quantities that people are interested in knowing because they describe kind of properties of the graph. They're kind of characteristics of the graph. The Lavash theta function is defined as the solution to a particular SDP. Amazingly, this lies in between those two NP hard to compute numbers. So this is what Lavash proved in 1979, that if you want to get some sense of the clique number or the chromatic number, you could actually solve this SDP and get something that's sandwiched in between those two quantities that are NP hard to compute. And that SDP is rather simple. It's just, look, this is just the sum of the entries of x. That's what the criterion is, subject to this very simple equality constraint on x. The identity times x is equal to 1. And x has to have all its off-diagonal entries equal to 0. No, not off-diagonal, excuse me. All of the entries of x that do not correspond to an edge have to be equal to 0, and x has to be positive semi-definite. So if you solve that SDP, then you get what's called the Lavash theta function. And Lavash's sandwich theorem tells you that it lies in between the chromatic number and the clique number actually of the dual graph or the complement graph of G. OK. That was very fast. We're not going to see that again in the class. I just wanted to bring it up because I thought it was interesting.
What is the y1?
1 is a vector of all ones. So 1, 1, t. Sometimes I'll write that with calligraphic ones. Yeah, this means the matrix of all ones. Just the outer product of the one vector with itself. OK, a more relevant, in a sense, to this class at least, SDP, is the trace norm minimization problem. So this is the analog to the sparse linear system problem we talked about at the start, but for matrices. Okay, so now I'm trying to find the solution to a linear, a system of linear matrix inequalities that's low rank. If all the matrices were diagonal, then this would be the same thing as finding a sparse solution to a linear system of equations in vectors. It's just a generalization of that idea. And we'll revisit this when we talk about matrix completion, maybe in 3 or 4 lectures from now. But this is an STP. That was our way of introducing it. This is an STP. So first, let's talk about what it means to have a system of linear matrix equalities. We're going to think about a linear map applied to a matrix, so script A of x, as just something that takes a matrix and gives you back a vector. And in each component of that vector, you're looking at the inner product of a particular matrix with x. So if you thought about how a matrix operates on a vector, it's really the analogy here, right? These would be like the rows of the matrix transpose x, but now we're in matrix world. So I'm taking the inner product of a matrix transpose x in each component. So given say a linear system of matrix equalities, script ax equals b, let's suppose we want to find the lowest rank solution to that set of equalities. And as we saw before, the rank function is very non-convex. So this is not a convex problem. The trace norm approximation to it, which again I'll just say once more, is the analogy of replacing the L1 norm with the L0 norm, replacing the L0 norm with the L1 norm, but for matrices, is to swap out the rank for the trace, which is the sum of the singular values of x. We learned that norm last time. Just remind you, the trace of x is the sum of the singular values of x. So we write singular values usually as sigma I of x and eigenvalues as lambda I of x. Here x need not be square, so that's why I'm using singular values. OK, this is an STP. It's actually quite intricate to show this. And I'm not sure that it's going to be very eye-opening to see it, but it might be something, again, that we put on a homework. I'll just tell you what the kind of flow is of the proof. You can always rewrite a norm in terms of its dual norm. So any norm I can write as the maximum inner product of a vector. So this is an equivalence we'll see when we talk about duality. If I have any norm, I can always write this norm as the maximum inner product I can achieve with x over all vectors y that have dual norm less than or equal to 1. So there's a unique norm that's called the dual of my norm. And this is actually the way to define the dual norm. So that's the way I can express a norm. And it turns out that the trace norm is actually the dual to the operator norm. So the trace norm, which is the sum of the singular values, its dual is the operator norm, which is the largest singular value. Okay. Again, if we make the analogy to Euclidean norms, this is like the L1 norm, which is the sum of absolute values. The L1 norm is dual to the infinity norm, which is the largest absolute value. So it's really a very tight analogy. Trace norm is dual to the operator norm. Therefore, I can rewrite this problem as the minimum over x as the maximum over y of y dot x for all y that have operator norm less than or equal to 1. And the set of y's that have operator norm less than or equal to 1, I can actually turn into a semi-definite constraint. That just involves a little bit of massaging. So that's how this is an STP.
Does it mean that we need to write the dual problem to show that this is
No, we're not writing a dual. We're just actually using duality of norms. We would just use this. The trace norm of x is the maximum over all over all y that have operator norm less than or equal to 1. So this means that the singular value, the largest singular value of y is less than or equal to 1 of y dot x. We would introduce this variable, and then we would rewrite the constraint on y having operator norm less than or equal to 1 in terms of a semi-definite constraint. I'm actually not sure I would put that on a homework just because it doesn't really I mean, it's specific to this problem, this manipulation. But if you're interested in seeing it, you can come to my office hours. I can show you the rest of the proof. OK. Now we have about just enough time to finish the rest of the hierarchy. Yeah, question?
So is the operator norm always the maximum singular value?
That's how we define it, yeah. Kevin?
Do you need this type of trick to show that QPs are SPs?
Close to it. We have that here. So we'll get to it in a few slides. We have just enough time to finish the rest of the hierarchy. So conic programs are the most general form of problems. And if you had an amazing solver for cone problems, then you'd be a very popular guy. Because almost every problem anybody ever wants to solve is a cone problem. And so, like I said, CVX and all these other general purpose solvers are all built on top of cone problems. Cone problems, they just take the linear inequality constraint, say dx less than or equal to d, and they actually just take that less than or equal to sign and they replace it with a conic less than or equal to. And what the Boyd and Vandenberg textbook does is it defines a bunch of partial orderings over cones and introduces like a new notation for less than or equal to, but for cones. I think that's a little bit confusing. So the way to think about it, I think, is just you have a cone k that you like, a convex cone, and you're enforcing the constraint that dx plus d has to be in that cone. That's all a cone problem represents, in place of the dx is less than or equal to d. So if this cone, if k was the non-negative orthant, then this would say that dx plus d has to be bigger than or equal to 0 in every component. That would give you back the LP. Okay, it's just a component-wise inequality on dx plus d. Instead of the non-negative orthant, if we took the positive semi-definite cone, we'd get back SDPs. Because we were saying that dx has to be bigger than or equal to d in a matrix sense. Okay, and here I would think about x and d as matrices rather than as vectors. The lowercase x and d. Yeah. I'm sorry? This statement? I mean, it's true for every norm in the sense that every norm has a dual norm that makes this true. Sorry? Yeah, it has to be a proper norm. But every norm is going to have a dual norm that makes this true. That's how we define the dual norm. OK, so cone problems are more general than SDPs and LPs because we saw we could recover SDPs and LPs just with two different choices of cones. And they can get much more glorious or terrifying depending on your perspective as you choose different kind of funky cones. A specific type of cone problem that's an interesting one is called the second order cone program. And let me draw that in our hierarchy so you can just get a sense for where that lies. This is what we're going to show in the next few slides. And if you forget everything from today's lecture and all you remember is this picture, then that's at least that's something. Just remember this picture. So second order cone problems lie in between QPs and SDPs. So that's how we're going to actually prove that a QP is an SDP. We haven't shown that yet. So a second order cone problem is an optimization problem where we actually choose as k here the second order cone, or the Lorentz cone. Remember we said that is it's the set of all pairs xt, where x is a vector and t is a scalar, such that the L2 norm of x is less than or equal to t. Remember that gave us that the ice cream cone shape, for example, if we saw x as a vector in R2. This actually corresponds to taking k to be the Cartesian product of a bunch of different second order cones. That's how you can see that this is a cone problem. But this particular problem is a cone problem, as we've defined in the last slide. But the general form is that, again, I have the usual criterion and equality constraints. My inequality constraints are that the L2 norm of some affine function, some matrix di times x plus vector di in L2 norm is less than or equal to some other affine function. Okay, so that's a second order cone program. And you'll see a bunch of examples in Boyd and Vandenberg about how people use second order cone problems. Turns out you can write some various types of covering problems, like minimum volume inscribing ellipse or something like that as a second order cone problem. But for our purposes, why I wanted to show it now is that we're going to use it to serve as the link between QPs and SDPs. And we're going to do that in a couple of steps. Yeah?
In the previous slide, you have mention of an EI. You're not talking about a standard basis vector, right? You're just talking about a random.
Sorry, EI is just an arbitrary vector. Yeah. Yeah, it's not the standard basis vector. So the first thing we're going to do is realize that every second order cone problem is an SDP. And to do that, we're going to use a little trick from the Schur complement theorem. And I'm going to claim that, that this is true, that x having L2 norm less than or equal to t is equivalent to the following matrix being positive semi-definite. The matrix T times the identity in the top left block, the vector x running down the columns, and then the last row is going to be x transpose in T. So I claim that these two statements are equivalent, so that I could think about now having a matrix variable and having a semi-definite constraint on the variable. This actually follows from the Schur complement theorem. So the Schur complement theorem is a handy thing to know if you're dealing with problems of these forms. It says that if you have a block matrix of the form A, B, B transpose C, then provided that C is invertible, this matrix, this block matrix, is itself positive semi-definite if and only if the Schur complement form is positive semi-definite. And that Schur complement form is this, A minus B, C inverse B transpose. So you can actually see this just from like a block matrix manipulation. You can write out what this means and get to that equivalence. So let's apply this fact from linear algebra to this. We just see that Ti x x transpose T is positive semi-definite, right? If T is bigger than 0, that's what C to be invertible means. If and only if the Schur complement is positive semi-definite. So that looks like this, Ti minus x x transpose over T, positive semi-definite. And I can also rewrite that as, right, just T squared I minus x x transpose, it's positive semi-definite. And now you can see that this actually exactly reduces to saying that the norm of x squared has to be less than or equal to t squared, because this guy is rank 1 and only has one eigenvector, and that's x, and it only has one eigenvalue, and that's the norm of x squared. So this is equivalent to saying that that's true. Because this one works. OK, so with this transformation, hopefully now you'll believe me that every SOCP is an SDP. And I'm like a minute over time, but I'm just going to tell you that every QP is an SOCP. So we may or may not just come back to this and do this last time. Maybe we'll just kind of skip it, and I can let you guys check that. But it provides us the link between QPs and SDPs, which gives us this picture, the one we saw at the start of the class. So like I said, remember that picture, put it on your office wall or something. It's nice to have as the hierarchy of all the problems that we're going to solve in this class.